Hi everybody, this is Mrs. Pinkerton and welcome to 2.2 Intramolecular Force and Potential Energy. When discussing this, let's revisit Coulomb's law. And Coulomb's law, remember, states that the force is determined by the strength of the charges, which is in our numerator, and the distance between those charges. So that's in our denominator of Coulomb's law. So chemical bonds are a balance between attractions, between our protons and our electrons, and repulsions. So those are our repulsive forces between two protons or two electrons. Coulomb's law is used to explain this electrostatic force between the electron and proton within an atom. It can also be used to discuss the attraction between a cation, remember that's our metal with a positive charge usually, and our anion, which is our nonmetal that forms that negative charge in an ionic bond. We're going to use this graph to show these attractive and repulsive forces. And notice this graph, when you're ever looking at a graph, you're going to read the y and the x-axis. And on the y-axis, we have potential energy. And then here on the x-axis, we have the internuclear distance. So that's the distance between the two radii of an atom, okay? So let's get this point of the graph where the two atoms are up here. We have really close distance between the atoms and the potential energy is really high. So at this point, the two atoms are too close together, causing repulsive forces. This is an unstable state as indicated by the high potential energy. So high potential energy meaning there's a lot of energy needed to keep this bond in place. And in nature, everything likes the lowest potential energy or a low energy state. It gravitates towards lower energy states. So remember that. Let's look over here at this point of the graph, at this little dip. And this is our sweet spot on our graph. At this point, the lowest part of the curve, the atoms are at an ideal bond length. There is a balance between the attractive and repulsive forces. So the attractive forces between the protons in the nucleus and the electrons, and the repulsive forces of the electrons on the outside of both atoms. It also shows the bond energy that would be necessary to break the bond. Potential energy is low, that shows stability. So why does a low potential energy show stability? Remember, and we'll learn, it takes to break. So we say takes to break. It takes energy to break bonds and free to form. When bonds form, it frees energy, meaning there's less potential energy once that bond forms. And that's ideal. The atoms want to be at a lower energy state. So think of like a ball rolling down a hill. If this were the hill, the ball's going to settle at that lowest point. That's that stable energy point, or marbles in a bowl. Again, they're going to settle at that lowest point. So think about that when you're looking at the ideal energy state. It's the lowest energy, okay? And finally here, we have the two atoms at this point of our graph. And notice the distance is really far apart. And again, we're talking about Coulomb's law here. And if the distance is too far apart, the atoms are too far apart, and they don't feel much attractive force. They feel little or no attractive or repulsive forces. So the potential energy is going to near zero. There's no energy there. There's no force combining these two atoms together. They're just too far apart. Let's talk about bond energy. And we use something called bond enthalpy, and it is the energy required to break a bond. or the energy released when a bond is formed. Increasing the bond order, and when we say bond order, we're talking about single bond, double bond, or triple bonds, increases the bond energy because the bonds get shorter. Increasing the atomic radii, again, decreases the bond energy because the bond length gets longer, okay? And again, that's back to Coulomb's law. The further apart, the less the strength is between those bonds, the electrostatic forces. So an example over here is this graph. We have potential energy and the distance over here. And you'll notice that an XY single bond is a blue curve. You'll see that the distance is further apart and the energy, the potential energy is up here, meaning it's not as stable, okay? And again, remember, the more negative, the more stable, the lowest energy is what we're looking for. The XY double bond has a shorter bond length and a larger bond energy. So it would require more energy to break that bond, okay? So what would a triple bond look like? A triple bond would be even shorter, right? And the energy would be even lower. So a triple bond would be shorter length, and the dip would be the highest energy, or the most negative bond energy here. So highest energy or lowest dip. I'm just going to put lowest dip there. Okay. So the most negative potential energy, meaning the most stable. But it would take more energy to break that bond. Okay, so to review, a single bond, we can draw with two dots like that, or one line. It has the weakest strength, meaning it takes the least amount of energy to break that bond, and it has the longest length. A double bond, again, we show it with either two lone pairs together or a double line. And the strength between a single and a triple bond would be in the middle, and the length would be in the middle as well. And finally, a triple bond, it can be shown with the sharing of these three pairs or three lines across. And it is the strongest, meaning it would take the most energy to break these three bonds, and it would have the shortest length, or the shortest distance between those two atoms. So let's look at some examples. The first example says the potential energy diagram is given for a carbon-oxygen triple bond. A student claims that the curve for CO would be less steep and would be shifted to the right of the curve for compared to this carbon-oxygen triple bond. Do you agree to this claim? Why or why not? So a carbon-oxygen bond would be a single bond, right? And single bonds are longer and weaker than a triple bond, right? So you would say, yes, I agree. So it would look like longer and shorter, and then we would bring that line up here, and that would be my carbon bond. And you could state again that a single bond is longer with less bond energy than a triple bond. And again, in good practice, if it says, do you agree with this claim? The first thing you want to say is agree or disagree. Okay? Us AP readers, when we're reading, we're looking for that I agree or disagree in your statement. So make sure you say that first. This graph, or this example, says use the potential energy versus internuclear distance graph here to answer the following questions. What is the ideal bond length between these two atoms? So I am looking for this dip, right? So this dip is right in the middle here. So I would say that that is about 75 PMs. What is the energy needed to break the bond between these two atoms represented in the graph? Well, now I'm looking on the potential energy side, and I would need to put in 400 and about 50 or 440, I don't know, approximately 450 kilojoules per mole to break that bond. This example, next example, a potential energy diagram for Cl2 is shown on the following graph. Based on the graph, what is the bond length in picometers for Cl2? So remember, we're looking for distance. We're looking for the dip. We're going to identify that. So we're looking at the lowest, which is 200. It says the student finds the average aluminum chlorine bond length is 220 picometers with the average bond energy of 425 kilojoules per mole. Draw the potential energy curve for that aluminum chloride bond on the graph. Well, I'm just going to graph it. I'm looking for 220 picometers with 425 kilojoules per mole. So 425 would be right below 400. I'm looking for 220, so this is 2, 4, 6, 8, 10, so that would be here, 425, so approximately here. And then I would draw my line coming down to the bottom. Oops, that's not a great curve, but going up, and it would look something like that. You'd probably want to make a straighter line going down, and it would look like that. Okay. This is a tricky question, this last one, and it's something we've seen on AP questions before. So it says the potential energy diagram shows a graph of potential energy versus internuclear distance for 3 diatomic molecules. And diatomic molecules just means a molecule, 2 covalent molecules bonded to themselves. It's hydrogen, nitrogen, and oxygen. And you need to identify which line corresponds to each. And you're going to justify your response. You will need to know how to draw or identify single, double, and triple bonds to do this question. And in section 2.5, we learn how to draw Lewis diagrams. Hopefully you've come into this class with some knowledge of how to draw a Lewis diagram. And in general chemistry, typically we just say, draw the dots. We're going to teach a different way in AP Chem, but hydrogen has 1 valence electron each, and so that's going to form a single bond. Nitrogen has 5 valence electrons. So here, let's go up here to our, and remember 1, 2, 3, 1, oops, 1, 2, 3, 4, 5, 6, 7, 8. Remember, we skip our transition metals. These are the valence electrons. So nitrogen has 5 and oxygen has 6 valence electrons. So nitrogen with its 5 valence electrons is going to form a triple bond, right? And then oxygen with its 6 valence electrons is going to form a double bond. So in order to answer these questions, especially if you're dealing with covalent molecules, you're going to want to draw out the structures and look to see if they have double, triple, or single bonds. And if you don't know how to do this or you don't remember, we will review this in 2.5. So I'm going to show you the structures here, and based off of these structures, which is which. Well, usually you'd be like, okay, the triple bond has the shortest distance, But notice here that the shortest distance actually has a lower or the lowest energy. But a triple bond, we know that has the highest energy. So is it this one or is it this one? Well, remember that hydrogen on our periodic table, if we go back to periodic trends, hydrogen is the smallest atom, the smallest atomic radius of all of our atoms on the periodic table. It's tiny. So that makes sense that if it's a single bond, it has the lowest energy, but its distance is small because it's a tiny atom. So hydrogen would actually be the X. Now we've got a shorter distance, highest energy. That's going to be our nitrogen. And then finally, oxygen is over here. It's in the middle, right? It's got a double bond. A double bond is in the middle. So that's going to be Z2. And justify your response. You could explain that hydrogen has a small radius. With a single bond. Nitrogen has the next smallest distance due to its triple bond with the highest energy. And when we say highest energy, we mean to break that bond. And then oxygen has a double bond and its potential energy would be in between the other two. Now, you could say this better in a different way, but this is just an example of how to explain your reasoning, and you can even explain it with diagrams as well. Okay, good luck.